at writes. Okay, in the last class we looked at reads. But before we proceed, are there any questions from the last class? Not about the project, but about the project we'll discuss a little later once we finish this. Okay, so let's look at the writes and see how a write happens and why a write can fail and what you should do to ensure that the write doesn't fail. Okay, so we'll kind of go back to our memory cell, which is the standard 6 transistor cell. So we have basically two back-to-back inverters. Then we said this is V cell. Okay, and then this storage nodes Q and Q bar can be accessed through these access transistors. And we have a word line which connects this. Then you have bit and bit bar. Okay, so now if you want to write into the cell, let us say the cell has a certain value. Let us say this is 1 and this is 0. Okay, and you want to invert the data into the cell. So how do we do how do we write an opposite value? So clearly you want to, in B, you want to basically, for the bit line B, you have to put a value of 0, okay, and you want to basically put a value of 0 here, and you put a value of 1 here. So what is done? Basically bit and bit bar are pre-charged high anyway to 1, which is VDD. And then you discharge one of them. So in this case, you discharge bit to 0. And then you turn on the word line. When you turn on the word line, if you look at the right side out here, Q bar is 0. So you will have, this is the same as what was happening when you had a read from the cell. Right, it will start discharging a current from B bar. But you designed your cell to be robust to flipping during a read, right? Because you designed it such that the this driver transistor is sufficiently strong compared to this access transistor. So this node 0 is not going to go up too much because you designed it to be very robust. So you cannot write a cell from the one side because you designed it very well to prevent the write from happening. So really the write for the cell will only happen from the 0 side. That is, when the bit line is 0, so what happens is you discharge. So now again what you have to ensure is that this node Q falls sufficiently low such that this inverter basically flips and Q bar becomes 1. So what that means is the pull-up device P and the access device, right? You need to set the relative drive strengths for that. So what you need to do here is that the access device has to be made sufficiently strong compared to the pull-up device so that this node Q comes closer to ground. Because when node Q comes closer to ground, basically this node is the input to this inverter, right? And that inverter will trip and Q bar will go high, and then the feedback will take care and it will store the opposite value. So really the writes will only happen if the drive strength of the access device mu a by La V word line minus V threshold is bigger than mu P, the pull up V cell minus VTH. So you need to have this condition guaranteed. Now certain things are in your favor. Typically the PMOS mobility, so you want NMOS to be stronger than the PMOS. So that's kind of easy to do. In most of the processes, the pull-up is PMOS whose mobility is anyway 2 times weaker, maybe 3 times lower. Again, it depends on the process. Okay, you have to kind of there could be certain processes where the PMOS is as good as the mobilities are as much as that of the NMOS. But nevertheless, you have to maintain this relationship. That is, the drive strength of access has to be sufficiently bigger than that. So usually what happens is that the PMOS, even if you keep it minimum sized, you use the minimum width for the PMOS. Then that is kind of sufficient for the PMOS to be weaker than the access device. So access device is also minimum width, and PMOS is also kept minimum width, but because of the relative ratios of the mobilities, PMOS turns out to be anyway weaker than NMOS, and so you will not have a problem doing this right. Yeah.
In normal operation, this PMOS is series with NMOS, which is down, pull down. When acceptor is not on. In that case, will this relation will cause any problem?
No, so the question is, when I'm not reading the cell, it's in the hold state, the access devices are off, will there be a problem in the cell when the PMOS is weak? See, what happens is that when the PMOS is weak, if you go back and think about the DC static curve, it is skewed because the pull on NMOS is much stronger than the PMOS. So in that sense, yes, so the butterfly eye will be lower than if both N and P were symmetric in size. So you will lose, yes, your whole noise margin will come down, right? But so you have to consider all of those factors of area, noise margin, and so on. Usually PMOS of minimum size kind of works well. And so typically you will have PMOS and access device minimum size, and then the driver device to be maybe 2 or 3 times bigger depending on the exact cell design. In fact, so I don't have the layout here, but if you recall the layout which I showed the last class of the flat cell, you will kind of see the sizing from that PMOS and the access are about the same, and then the NMOS is a little bit bigger. It's not 3 times bigger, it's a little bit bigger, I think. Now what happens is that you can do something more to improve the writes. Which is you can it's apparent from these equations out here. What do you think you can do? You have done whatever you could in terms of sizing. NMOS is minimum size, okay, because you don't want to increase the access device size because then it will compromise the read stability. So you have used the minimum size, and PMOS also used minimum size, but still you find that writes under certain conditions are not happening. So what more could you do? If you look at the equation. So you have one more parameter here, right, which is in your control. Word line and V cell. Okay, so you have those two parameters in your control. So you could either to do the right increase word line only for write, or you reduce the V cell. So you could do, that is an additional thing you can do.
So these are just the possibilities, or these are the things which done in the circuit?
Yeah, this is also.
There are variety of voltages should be provided for the single chip.
Good question. So the question which is being asked is, how practical is it to use these different voltages? Because you need to supply those voltages on chip. Okay, that's a very, very valid and important question. Now, what happens is that, uh, you know, you're at a point where you did whatever you could and now you're still not able to write. Okay, now you need to enable the write. I mean, you need to allow for write happen. So then you are forced to look at this additional variable of v cell or v word line. Then you have to figure out how to generate these additional voltages. Now, if these voltages don't draw too much current, that means you don't load these supplies, then it is pretty straightforward to generate these voltages on the chip itself. Whenever your voltage source needs to supply a lot of current, then you really need to go, the design of that voltage source becomes, it kind of becomes difficult to just do it using only on-chip components, because you need to go towards more what you would learn in power electronics. Probably you need to go for buck converters and those kinds of things. But on chip, if when the load requirements of the power supply is small, you can use on chip. There are various circuits which will allow you to generate these on chip voltages. So one thing which is done is, maybe I should. Okay, so before we do that, let's look at the issue of noise margin. Okay, so similar to the read case, we can also define write noise margin. So again, you take a half cell like this. Now in the case of a write, what is happening? One side of the bit line is kept precharged to VDD, the other side is 0. Right, so your two half cells are not the same. And so you look at one of the half cells and you look at input and output of the inverter. You see that the output of the inverter is being pulled low by this structure out here. Okay, so this, so then you end up with this kind of a curve where the VO, when Vi is 0, VO doesn't go all the way to VDD. Okay, because VO, when Vi is 0, there is a PMOS which is connected to VDD, but this NMOS, the access device, is holding it to ground. So this is really that. So in fact, this is a cartoon sketch, but really you want this to be kind of even lower. So this is that device, the transfer curve of this. And this one is a transfer curve of the other half cell, which looks like a read transfer curve. So that is why and it's kind of reflected, so it comes like this. That means this one doesn't. VO is the input. When VO is VDD, the NMOS is on, but then it's fighting with the access PMOS, access NMOS, which is connected to VDD, so it doesn't go all the way to ground. See, this is the ground here, because in the case of the other half cell, this is the output, this is the input. Okay, we have reflected by 45 across the 45-degree line. So now if you see out here, this pair of cells together, when connected together, they have a single consistent operating point here, this point of intersection. That means there's only one valid operating point for this cell. When you didn't have this, when you didn't turn on the word line, you had the butterfly diagram where you had 3 possible points, 2 at the 2 extremes and 1 in the center. The center one is of course the unstable point. If you push it, then it goes to one or the other. Here there's only one. This is what you want, because you are forcing it to be in a one particular state. And then when you remove the access device, remove the word line, it will stick to the same point here. Okay, but the problem is these two curves touch each other or cross each other. Then again you have possibilities of multiple consistent points, not only one. So then you don't know which one it will go to, and it might end up not writing the value you want. So that is why this spacing out here is the noise margin, the spacing with the two curves. If they collapse and there is no spacing or they intersect, then you know that you are in trouble. So that is basically a way by which you can, so you can again look at the minimum, the square, the smallest square, which will, imagine that you have a square which you are sliding across this, and such that the two endpoints of the square are on these two lines, and then you have to keep shrinking the square. It reaches the smallest size, and then it starts going big. So that smallest size, you can say, defines the right noise margin. So as we said, you can improve the noise margin by increasing the word line VDD to strengthen this device so that this pulls down even more, or you reduce the cell VDD. Okay, that is another way. Because cell VDD, when you reduce, what it does is it weakens the PMOS. With which this is good. So again, you'll pull this thing down. Now this concept of using a lower V cell is actually, you see this paper from Intel, so they report this approach in one of their experimental chips. It's a 3 GHz 70 megabit chip with 1.1 volt supply. It's not very, is it clear to you from the back? So basically what they have is, in this memory array, the cell VDD is going vertically, that is the line in the center. Okay, and then the bit line, these are the two bit lines, and this is the word line which is running horizontally. What they do is during a write, so they have two supplies, high and low, and the cell VDD is essentially driven through that mux. So so the VDD line here acts like just any other signal line. Okay, and then you kind of mux between these two. The reason you can do this is that the current drawn from the VDD line, the VCC line here, is very small. The cells are tiny, and you have many of them, of course, in a particular, each column has its own VCC line. Okay, see, normally you don't want to do this kind of thing because this mux will put in additional series resistance and really degrade the operation of your circuits and so on. But in this kind of situation where the cells are largely static, they don't switch much, they don't draw too much current, and the only current you draw is when there is some leakage current, of course, and when the cell, you're writing into the cell, there is some current, of course, and reading also there is some current, but these drawn from this vertical line, but the currents are very small. They are in the few microamps range, 20, 30 microamps. And so you can kind of just do the simple thing of having two supplies, and then you have a mux to select the supply. So during a read or a hold operation, you supply the VCC high. During the write operation, you supply the VCC low. So what that does is it weakens the PMOS and allows you to write properly.
So basically special kind of mux.
Yes, normal mux.
Normal mux low.
But I need to work for 0 or means there is no direct connection between the input and output.
No switch, no sir. We have a separate, there are AND or gates. No, AND gate has
Sorry. The question is, okay, let me repeat the question. The question is it a normal mux? Now, of course, what is the definition of normal? We don't know. It's basically on the right side you see this, right? Basically what you have is the mux essentially consists of two PMOS transistors. That is sufficient. It's like pass gate. Because you are passing only the high value signal, you don't need the NMOS. So that is why you have these two PMOS transistors. And one thing you notice out here is the substrate of the PMOS. Where is it connected to? It is always connected to the highest supply. So the substrate of the PMOS is connected to VCC high node out here, right? Because the PMOS body should be at the highest voltage in the circuit, right? Otherwise you will turn on or forward bias the P and die.
So we are using body effect, we are controlling the supply.
Right. No. Body effect, we are not controlling the supply. Body effect, these substrate nodes are just connected to a fixed supply. Okay, VCC high. But VCC SRAM out here is connected either to VCC high or VCC low, depending on the value of VCC select.
So we are doing voltage splitting.
You can say this is kind of like, yes, an example of power gating, but not but there are two different power values. You are kind of modulating the power supply.
So you have shown a lot of marks.
Lot of muxes, one per column, yes.
That means each column voltages can be controlled.
Okay, so that is each column voltage can be controlled, but it's the same value. You don't give different voltages to different columns. Because again, you come back to this problem of generating those voltages.
So we can use body effect also. We have two different algorithms. Like correcting body to zero in an NMOS, normal NMOS. Correcting body to zero equals correcting body to VDD. Same as VTH. Threshold voltage. So when you are passing one through NMOS, you get VDD minus VTH. If you are changing VTH, then
Correct. So the question is basically, can we not modulate the threshold voltage? Because if you go back to that equation, it was V cell minus VTH. So why not modulate the threshold voltage of the transistors? So now the threshold voltage and the body voltage, that relationship, right? There is it turns out there is about 1:10. That means if I want 100 millivolt change in threshold, I need to have about 1 volt change in the body voltage. Because, and in fact, the processes as we go down, we want to have less and less impact of the body on the threshold. Because you want to have only the gate to be the main controller, master of the channel. So the body's influence on the threshold voltage in deep submicron is much less. So, so you have to really put in lot more voltage to get 100 millivolt. Not series of MOSes. There is one MOS whose body you have to, if you change by 1 volt, the threshold will change only by 100 millivolt. Okay, so that means that, and body is again a capacitance, you have to charge and discharge that capacitance by that large voltage, so you are going to burn power for that. It is exactly less sensitive. The body influence is less. Here you can directly modulate the supply voltage because these cells don't draw too much current from that supply. So it's kind of relatively straightforward to do this. Okay.
So we can have a single mux and the output goes to all the columns.
Correct. You can have a single mux and the output can go to all the columns. Now, there is a notion of resistance of these muxes, right? Because this mux introduces a resistance and there is a certain maximum resistance you should put out there. Okay, because even if because even when there is always some leakage current. That means, so let us say you are in the hold state and you have put VCC high. Okay, there is some leakage current, and that leakage current will flow from the VCC high through the mux into the cell, and there are so many cells. So leakage of one cell times n cells in the column, that is the leakage current, and that will lead to a drop in the mux transistor here. So that means the effective voltage to the cell will be less than VCC high by that drop. You don't want the drop to be too large because then the cell voltage becomes less during hold. And for hold and read, If you recall, you want to have a high cell voltage for good noise margin, whereas for write you want a low cell voltage. So that means there is a certain size, minimum size you want to have for the mux. So, and then that size, when you have so many columns in parallel, you have to take all that account, and you have to have so many, that size mux. Now that size mux, how will you lay it out? It's much easier to lay it out like this. Each piece has its own little thing. Because anyway you have to have that big a size, right? You need to have so many, so you just do it this way, and then this has a benefit that tomorrow you want to increase the number of columns. This whole column you have one module, as a module you have done the layout, you have figured out the right sizing, you just stamp one more and you are done. Otherwise, it becomes messy. Question? Yeah. How do we generate two different voltages? How do we generate two different voltages?
So can we use two models like this? One situation we are passing VDD to PMOS, and in another we are passing VDD to NMOS. So we get VDD at one end and VDD at VDS at another.
Right. So so one of the suggestions is, why not for VCC low, generate VCC low by having it pass through a NMOS. So you have a threshold drop. Okay, so what you have is you have VCC high. See, this is coming from your external power supply and it goes, and then here you have again VCC high, and so this voltage will be minus VTH. So you have a VCC low. So this is the suggestion. Now there are two basic problems with this. One is that see, this drop of this output NMOS voltage being VCC minus VTH. If you really wait long enough, because you always have some subthreshold leakage, right, through that. So that leakage, So that leakage will slowly charge up this output. Of course, you have to wait a long enough time, but then you are running this memory, in a few seconds, it will just charge up all the way back to VCCI. So that doesn't work that well. So if you want to use this NMOS, so what you have to do is periodically you have to discharge it. So you might have to have a setup where maybe there is some other circuitry which is like a reset, right, and then it resets it. So then it kind of becomes a messy thing. So what happens is, if you look at this voltage here, it kind of goes up and slowly it's going up, then you reset, then again it goes up, then reset and so on. So it's not doesn't work well. That is one problem. Second problem is, this guy, if there is some load circuit out here, because you have to be able to supply this, if there is some load out here, right, that is drawing a certain current. A power supply ideal power supply should be able to supply any current. Real power supply will have some impedance, right? So that is where because as soon as you start supplying current from there, the voltage of the supply starts going down. So, how good is this impedance looking out here into this, right? Because this NMOS is almost off. Even at VCC minus VTH, it's off. So it doesn't have a low enough impedance. So it's not a good supply. So you don't want to use this. But you can probably, if you had, you could use this to. Okay. So what do? You can have. You can use something like this maybe to give a reference. For example, if people who are doing analog circuits class would be able to maybe think of a solution, but let's see if we can do something here where maybe you have Um, this gives me a reference, and but then you need to have a little circuitry which will do the buffering and drive it, a low impedance thing. So you can use something like this to give you a reference and then drive. Now, so what this is an op amp which drives it, right? So this could be one way, and then there are other ways. There are capacitive based uh, structures and so on and so forth. So, okay, if I want to reduce supply, you can use something like this to generate the VCC load. Now, if you want very precisely controlled voltages out here, right? You want to have, see this one, what voltage will we have? If you size both NMOS to be the same, this voltage will be somewhere in between. VC low by 2, which might be okay. VC low being VC high by 2 is okay. But we want some voltage which is some 100 millivolts below VCC high. Then how will you do it? That could be one way. So one thing you have to remember is that if you use sizing, then you have to try to keep things similar to each other. Otherwise, when you size it, you are relying on the ratios and a certain matching. So you will have to kind of, for example, if this has a size 1 and this has a size 4, maybe you have 4 copies of this. So then you will have basically you can kind of say approximately that this has 1/4 the resistance of this, which is not exactly correct because I think we are getting into too much of analog discussions here. So I'll just stop here. But something like this you'll have to do. Okay. Okay. So the other way which people do is to reduce the supply is to this is another approach which was proposed. So here you see the memory cell is a 10 transistor cell. Okay, this cell was proposed so that the memory can work down to very low voltages, maybe 200, 300 millivolts kind of thing. So that is why what they have done is, as we discussed in the previous class, they have a separate buffer. They don't allow the read current to go through the cell. There is a separate read buffer. It kind of looks complicated, but really it is a read buffer. We will not go into details of what these two transistors are doing, but essentially this is just a separate read buffer. Now in this particular cell, what they do is, when they want to write into the cell, they just here the VDD is going horizontally per row. In the previous Intel design it was going vertically per column. Here it's going horizontally. And that particular row, and each row the VDD is connected through this PMOS device. So you just disconnect the VDD line. So it's left floating. The VDD is left floating. So the PMOS is kind of left orphaned in some sense. Like the VDD is no longer a stable VDD. It's just left floating. So the PMOS is not able to fight well with the NMOS, and the access device wins, and you can write into the cell. Okay, and then you turn on the you put the data. Okay, you turn on the write, you disconnect the VDD and it writes into the cell, and then you turn on the VDD and then it remains the virtual VDD is floating. See, what happens is, when it's floating, it's like a capacitor, and it basically holds the because the cells are drawing current, the voltage on this virtual VDD starts coming lower, the PMOS becomes weaker, and then the cell is able to get the new data, and then you pull it back up. Of course, here if you see, this VDD is it's shared between the two rows, but you write only in one row. So the row which you are not writing, but it's connected to this, for that duration, brief duration, it sees a lower VDD. for that duration, just the one row above you. In the previous approach, in this Intel approach, the entire array sees a lower voltage. Even though you are going to write into a single row, the whole array sees a lower voltage during that period of write. So you are making the whole array potentially more vulnerable. Of course, that's for a short duration. So hopefully during that duration, the cells which you are not writing, their noise margin has come down because you have reduced the voltage. So they can become potentially more vulnerable during that time. Like here, only one additional row is made vulnerable. Now you can say I will have separate VDD for each rows. So then you make that even more robust. So only the row you are writing, the VDD reduces, the other rows remain where they are. But that means extra area. The reason they have done it this way is they are sharing this. Okay, so memory cell. MC is the memory cell. Whole noise margin, which is large. Exactly. So that is why they are willing to get, but they take a hit in the noise margin. The noise margin of, if during that time, for example, as we discussed in last class, there is a particle strike, right? It is more chance of it flipping the cell. So we look at the, so if you look at the column, you have you have these memory cells in a column, and then you have this pre-charge circuitry. Now what is the pre-charge circuitry, right? I'm showing 3 transistors here. The goal of the pre-charge circuitry is, there are 2 things. One is it should get the bit lines pre-charged to VDD, and more importantly equalize the bit lines. We'll see that because when we do, when we want to speed up the read access, we basically use what is called a sense amplifier. During a read, one of the bit lines pairs, one of the bit or the bit bar starts discharging. You can wait long enough and it will discharge all the way to ground. Simple inverter will tell you the value. But these cells have very small currents, and when you have large memories, these bit lines can be large. The capacitance can be large, maybe half a puff, and the cell current would be maybe 20 microamps. And if the voltage is 1 volt, so you can do CV by I to figure out how much time it takes to discharge it, and it will be pretty large. So you can't wait for the bit line to discharge all the way from logic high to logic low. You can't use a digital type approach to get the read data because it is too slow. It will slow down your access because you really want speed. So then what you do is you have something called a sense amplifier, which will, even when there is a small bit line differential, maybe 100 millivolts, the sense amplifier it's sufficient for the sense amplifier to make a decision as to what is the value. Okay, we'll see that next, how that sense amplifier works. But really it looks at the difference between the voltages of bit and bit bar, which means that before you start the read, you better make sure bit and bit bar voltages are close to each other, because any residual mismatch, maybe in the previous cycle you did a write where bit line bar was 0, because during a write you discharge all the way to ground. Bit line bar is 0, bit line is 1, and then you equalize. So bit line bar comes up, but maybe it doesn't come up fully. Maybe it has just come up 100 millivolts short. And the next cycle you are doing a read where the other one is supposed to be going low. You see 100 millivolts is kind of the signals anyway we need to sense. So if you start off with minus 100 millivolts in the other direction, it is not good. So equalization is important. So that is what this transistor does. It shorts bit and bit bar. In addition, you have these 2 PMOSs which pulls bit and bit bar to VDD. So there are 3 transistors. Okay, in the textbook they are not showing this, but this is a very important transistor, equalization. Anytime you have differential circuits, comparator type circuits, you need to make sure you have that equalization transistor to equalize, so that you erase the memory of what happened in the previous cycle. Okay, now here in addition I am also showing the column circuit. It's just 2:1 column mux. Just a simple PMOS based mux is sufficient here. Because the voltages we are going to deal with for reading is all close to VDD. So PMOS is good, essentially good to send anytime signal is close to VDD. If you want to pass it to a pass gate, you want to use a PMOS transistor. Because PMOS passes high voltages well. So this is the column circuit. So you turn on a word line and you select one pair of columns in this 2:1 mux and take the data. The signal comes to SBL bar, then it goes to the sense amplifier. So this is the sense amplifier which is used pretty much now in all memories, SRAMs and DRAMs, and probably other memories also. So this is what is called a clocked sense amplifier. Okay, let's see how this sense amplifier works. It looks like a memory cell. Basically, there's two cross-coupled inverters, except this node, instead of being ground, it's connected to ground through this NMOS device. So SBL bar which come in, and there's also these two PMOSs here. So SenseAmp enable is initially low out here. Okay, that means these two PMOSs are on, and I've missed out something here. These two PMOSs are on, okay, and then you have basically initially both Q and Q bar are VDD. Before you do the read, Q and Q bar are at VDD. Okay. As the word line turns on, the bit and bit bar start falling, and depending which column you select, SBL bar also will start tracking that, and they start falling. As soon as you have enough differential voltage, usually about 50 to 100 millivolts, what you do is you turn on the SenseAmp enable. When you turn on the SenseAmp enable, basically the SenseAmp amplifies this difference to full logic levels. The small 100 millivolts gets amplified to VDD and ground. Okay, how does that work? How does this amplification work? Basically, let us say in this example, I have not said, okay, so let us say Q was lower than Q bar by 100 millivolts, right? When SenseAmp enable is low, it's about to turn high. SenseAmp enable is about to turn on. Now, what is this voltage X? This voltage is at what voltage value will that be? That voltage will be basically at about VDD minus VT, right? Because that node is getting charged through these NMOSs. So it's about VDD minus VT. It's not fully VDD, it's VDD minus VT. But it's a common voltage to both these NMOSs. Now when this turns on, what is happening to this voltage? This voltage starts falling to ground. Right? As SenseAmp enable goes high, this NMOS starts turning on. So this common voltage starts falling to ground. As it starts reducing, what will happen is both these NMOSs will start turning on. Right? They are both off. That's why this is at VDD minus VT to begin with. But as this starts falling, both will start turning on. But you see, one of these is lower than the other. Q is less than Q bar. So Q, which is the gate voltage for this, means this transistor has a lesser gate source voltage than this transistor. So he will turn on less fast than this guy. The guy on the left will turn on faster because he sees a larger gate voltage Q bar. And you see it's a self-fulfilling thing. Because he sees a larger voltage, this Q will reduce more rapidly than this Q bar. This is basically positive feedback. You already started off with Q less than Q bar, but because of that condition, Q starts falling more faster than the Q bar, and that's what basically happens. This is the positive feedback, and if it falls sufficiently low here, Q bar, this PMOS turns on and helps to bring. As Q falls sufficiently low here, then this PMOS turns on and Q bar gets pulled up back to VDD. Okay, initially both of them will start falling because this node starts turning on and Q and Q bar start falling. But then once the PMOS turns on, it kicks and puts this back to VDD. So this is what is called a clocked sense amplifier. One thing you also notice is when sense amp enable goes high, these PMOSes are shut off. So what that does is it isolates Q and Q bar from these nodes SBL and SBL bar, which in turn are coming from these pass gates and these bit lines. Essentially you isolate the sense amp from the bit lines. So you wait, you capture the data in Q and Q bar, let the differential set up, and then you turn on the sense amp enable. You disconnect, at the same time you disconnect the internal node from the heavy capacitance nodes. The amplifier amplifies, and then you pass it through an SR latch here because you want to hold the data, because as after some time you want to disable the sense amp enable and get it back to ground to reset it so that it's ready for the next cycle. But you want to then hold the data, so you have a simple SR latch out here which holds the data. So this is basically how this clock sense amp works. Very simple structure but very effective, and pretty much now this is what is used for all memories. Okay, very power efficient structure. Q and Q bar will be at what value? It will be at SBL, SBL bar, which are pre-charged to VDD. Exactly. Now you can in addition put pre-charged transistors here, but you know, depends on the detailed structure how you do it. But essentially they start off with VDD.
So this is not the memory cell. This is in addition to memory cell.
Exactly. This is there below in the column out here. See, this whole thing up in the top is the memory array. These are the column circuits. This is the pre-charge circuit. This is the column mux, and below here is the sense amp, which I am showing in the next page. So you have one sense amp per bit you are reading. Okay. How is the enable generated? So that is the next question which we'll discuss in the next class. But I'll just flash this and then I'll come back in the next class. Because now one important thing is you have multiple signals out here. Let's look at the complete memory during read. You have a clock. Usually these memories are all synchronous memory. They are embedded in a synchronous chip. So there will be a clock which starts the access. After some time word line goes high. After the decoding the word line goes high. But before the word line goes high, you have to shut off the pre-charge. Because pre-charge was keeping the bit lines high. But you need to disable the pre-charge so that the bit lines become floating. Then the bit and bit bar start falling. At the right time you need to give the sense amp enable. So how do you manage all this timing? So like this is something which has to be worked out. So this is something we'll discuss in the next lecture. Okay, any other questions?